Good day and welcome back for part 5 of our discussion on enclosed areas. Let me begin with a reminder from our previous video. If we would like to calculate the area enclosed, let's call it A, between the graph of a positive curve and the x-axis from x equals A to x equals B, we can do so using the following method. We saw that this area A would be equal to the limit as n approaches infinity of the following sum. The sum from I equals 1 to n f of x sub I delta x. And we certainly need to define a few of these terms. Recall delta x is equal to b minus a over n, and x sub I is equal to a plus I delta x. And this is precisely where we left it in our previous video. What we will now do is apply this idea to one more additional example. Let's find the area enclosed underneath the curve given by x cubed from x equals 0 to x equals 3. And if we were meeting in person, this is where I would turn the floor over to you. I would give everyone 8 to 10 minutes to work through this problem as I walked around and interacted and answered questions. Unfortunately, we are unable to do that at the current moment, but what I would like you to do is to pause the video, give yourself that 6, 8, 10 minutes, whatever it requires, and see if you can complete this problem. Once you've put an honest effort into it, come back to the video and compare to the rest of our solution. So we're going to start by just cutting and pasting the formula from above. So this area that we're trying to calculate would be the limit as n goes to infinity, the sum from I equals 1 to n of f of x sub I delta x. And similar to when we were working with the definition of the derivative at the beginning of the semester, I joked that I always start by writing out this general formula because that means I always know what my first step is going to be. And similarly, I always know what my second step will be as well, because I need to substitute in these specific quantities. So for this problem of interest, we know that f of x is equal to x cubed. Delta x is going to be b minus a over n. Well, a is going to be this smaller value of x. B is going to correspond to the larger. So 3 minus 0 over n, which is 3 over n. And x sub I is equal to a plus I delta x. So 0 plus I delta x. So I'll say 3I over n. And even furthermore, we can calculate to the side f of x sub I, which we need in our sum, is going to be 3I over n cubed, which we can certainly write as 27I cubed over n cubed. So in terms of the quantities we need to rewrite, we have f of x sub I and delta x. Let's go ahead and substitute those quantities into our sum, see if we can use our common formulas we've previously introduced, and then calculate the limit. And note at each step along the way, we're going to organize this in a vertical column. We're going to include good notation, writing limits, summations, until we have calculated those quantities. So this is the limit as n goes to infinity, the sum from I equals 1 to n of 27 over n cubed I cubed from the f of x sub I multiplied by 3 over n. Now we can kind of go ahead and combine together a few of these terms. Note the 27 over n cubed and the 3 over n have nothing to do with I. So we could go ahead and, in a sense, multiply those two quantities together and pull them out front of the sum. Note, we certainly cannot pull them out in front of the limit because they involve n, but they can sit in between the limit and the summation. So this would be the limit as n approaches infinity of 27 times 3 over n to the fourth multiplied by the sum from I equals 1 to n of I cubed. And immediately, this is looking much better. And the reason I suggest that is the sum from I equals 1 to n of I cubed is one of our common summation formulas we introduced in part 1 of this discussion. And the associated formula that we should make sure to recall, as it will also come up in our next topic, is that this is the quantity n times n plus 1 over 2 all squared. And when it comes to evaluating this limit, note we can go ahead and really more or less do this at once, but I'm going to take one more step just to make it as clear as possible. So making this a single fraction and remembering that we do have this square that we need to take care of, in the top we would have n times n plus 1 quantity squared times 81, and in the bottom we would have 4n to the fourth. And when it comes to evaluating this limit, I want to note the same observation we made previously. This is a rational function in terms of that variable n. We have a degree 4 in the bottom, and if you want to, you can expand out in the top. It's degree 4. So the value of this limit as n approaches infinity is simply determined by dividing those leading coefficients. So the value of this limit and the area that we've been asked to calculate is 81 over 4. And once again, just to kind of recap, as this is a type of problem we will be doing multiple times in our next section as well, this is roughly what you should expect your work to look like. A nice vertical column using good mathematical notation, proceeding logically from one step to the next. And this finishes up our discussion of finding enclosed areas, but certainly make sure to take some time and work through suggested problems in the textbook. When you have questions, stop by or drop me an email. Stay tuned and take care.